Hi, my name is Sierra, and today I'm going to be presenting MSDBench, Understanding the Performance Impact of Isolation Domains on Microservice-Based IoT Deployments. So, historically, applications have been made using monolithic application architecture, which is when all of the functionality is integrated into one piece of kind of one giant piece of code. And now microservices application architecture is this newer architecture where you pull out specific functionality into very independent, more loosely coupled pieces so that you can modify and update and test each specific functionality more specifically. And also, the Internet of Things is when you have a bunch of different devices that all might have very different types of memory or amounts of power working together and communicating over the network. So we hypothesize that microservices application architecture will lend itself really nicely to this very heterogeneous environment. But in order to do that effectively, we need a way of evaluating where should we actually put each microservice and what happens to performance when we do so. So to be clear, we need a benchmarking suite to be able to understand how, one, the microservices technology, meaning the operating system and RPC framework, which is how the services communicate, and the isolation mechanism support different deployments of microservices in IoT, and then also how the specific deployment, meaning how you end up isolating the services from one another and where you physically locate the services, affects the performance of microservices in IoT. To do this, we need a benchmarking, or this benchmarking suite needs to consist of micro benchmarks, which isolate the performance of a very specific task, in addition to end-to-end benchmarks, which do a whole request type. And the two of these paint a really good picture of what's actually going on. So MSDBench was developed for this purpose. There we have micro benchmarks, which literally consist of just two services that one calls the other in order to target the inter-service latency. And then also end-to-end benchmarks, which to do this, we have an application called Best Effort PubSub, which was basically designed to be very representative of common microservices architecture design patterns. So for Best Effort PubSub, we have a client service that makes requests to a load balancer, and then the load balancer services the request using some number of the other microservices. We also compared two technologies. So the first set are the commonly used technologies already for deploying microservices. So the operating system is Linux, the RPC framework, which is the technology that's used for services to talk to each other, is Thrift, and then the isolation mechanism is Docker containers. The second option that we looked at is this much more experimental option where the operating system is Ambience, the RPC framework is Little, and the isolation mechanism is Ambience groups. And all of these are highly optimized specifically for running microservices in IoT. So this was also a little exploration on this comparison. So when I say we have a lot of deployment decisions to make when we run microservices in IoT, there's kind of two parts. The first is how you're going to isolate or co-locate the services within what we call isolation domains. So this is either the Docker containers or the Ambience groups. So we tested 3 different isolation domain configurations. The first is called co-located, when all the services are in the same container together. The next is called tiered, when they're separated out into 3 different containers. And then the last is called isolated, when each microservice gets its own container or group. We also have to decide where to put the services. So that means where they physically go in terms of which machine they go on. So deployment 1 is when all the client service is in the same isolation domain, in the same VM, on the same host as all the other services. Deployment 2 is when we pull that client service and its container or out into a separate container with respect to the server-side services. Deployment 3 is when we pull that client-side container out into its own VM, but still running on the same host as the server-side services. Deployment 4 is when we pull that client VM all the way onto a separate host. And then deployment 5 is finally when that client-side service runs directly on the second host. So this, we also made, these are very incremental changes between each deployment variation, so we can really target how the difference affects the performance. So first, looking at the ambience results, this upper left graph, on the x-axis are all the different request types made by the client, and then the y-axis is the average round trip time to perform that request in microseconds. So, and then we can also see we have the co-located, tiered, and isolated isolation domain configurations for each deployment. So overall, for ambience, compared to deployment 2, which is again, when the client-side service is in the same VM as the server-side services. Deployment 3, which is when the client-side service is pulled into its own VM, but still on the same host, is 3 to 4 times slower. Deployment 4, which is when that VM is pulled onto a separate host, is 13 to 23 times slower. And then deployment 5, when that client runs directly on the second host, is 6 to 8 times slower. Down here, there are the micro benchmark results, which is again the time that it literally just takes one service to call a different service. And on the x-axis, this buffer size is how much data we're passing in between the services, and the y-axis is the average call time. So when the services are co-located for ambience, that means they're put in the same ambience group, and it's highly optimized so that there's zero copying. So this buffer size actually, has no effect on the latency, and it still has very little effect on the latency, even when those services are separated out into separate groups, because ambience still performs a lot of optimizations. Looking at Linux, compared to deployment 2, so again, this is the same graph that we have where we have all the different request types, the round trip latencies on the y-axis. And so to compare to deployment 2, for Linux, deployment 3 is 14 to 16 times slower. So moving that client side into its own VM has a much more dramatic hit. Deployment 4, which is when we pull that client VM onto a second device, is 65 to 68 times slower. And then deployment 5, when we run that client service directly on the second device, is 45 to 56 times slower. So the same relative relations in terms of what's slowest to fastest are true, but the performance hits with Linux are much more dramatic. Also, for the micro benchmark results, you can see as the buffer size increases, the time it takes for one service to call another service also increases linearly. And that is because Thrift serializes the data when it passes it. So no matter whether the services are in the same container or separate containers, that same serialization still is happening. So now this is all of the results, but things to notice is ambience is on average at least an order of magnitude faster than Linux for all equivalent deployments. And also the slowest ambience experiment across deployments 4 and 5, which is the ones when ambient or the client side is on a separate device, are faster than the FastX Linux experiments in deployment 5 across all of the experiments, regardless of the isolation domain and service request type. So it's really just showing that ambience's optimizations for this purpose really do have a dramatic effect on the performance in terms of latency. We also have the capacity. We did capacity tests where we tried to find the saturation point in terms of requests by increasing the number of clients. So for ambience, this saturation point happens at around 57,000 requests per second, and then it just kind of plateaus. Whereas for Linux, it couldn't even get to 10,000. And then as soon as you get above like 15 to 20 clients, the Linux application just crashes. So this capacity is also much, much lower in this with these technologies. I'm going to quickly say, we also were able to run the microcontroller. We were able to run the ambience tests on the microcontrollers because ambience is able to run on the microcontroller, but the option 1 technologies are not. And basically as soon as you pull the services onto 2 different devices, the client onto a different device, you get this huge performance hit, which makes sense because microcontrollers are much more resource constrained. So communicating over the network is really hard. And then the micro benchmarks, again, you have that same pretty big performance hit when the services are not located on the same device yet. Actually, this is just if they're not in the same group, but it still is much slower if they're not in the same group. Okay, so in conclusion, MSDBench compares operating systems, RPC frameworks, isolation domains, deployments, meaning where to put everything, and then the IoT devices themselves, because we looked at cloud and edge devices and microcontrollers. We specifically evaluated performance in terms of latency and client capacity, and our results clearly show that the inter-process communication does matter, and also the deployment and deployment technologies that you use affect performance. All right, that is